welcome to the week 6 discussions on of the course Fundamentals of Conduction and Radiation. And as you guys know, this session is a rescheduled session that we are hosting today because of the postponed session of previous week, which was actually week 6. And the current week's discussion will be done on the usual timing from 3 to 5 on Saturdays, that is on tomorrow, which is the week 7, that is the ongoing week. So today's class is about the previous week's discussions that we saw, and what follows we will look into some of the aspects of the problems given in the assignments through certain problems, which majorly focus on 2D heat transfer, as we will see very shortly. And tomorrow is we will discuss transient heat conduction, which is the agenda for week 7. Okay, so let's begin. So as I said, we will look into the concepts of two-dimensional heat conduction, and in particular, uh, so we will be solving problems using an analytical tool which is known as the method of separation of variables. And I hope you have learned the basic aspects of separation of variable in from the lecture series, in which there was a detailed discussion on how to apply this method for solving, in particular, certain kinds of 2D heat transfer problem, where we will see very shortly that what the governing equation should be and how the boundary conditions should look like in order to use method of separation of variable. So until this week, that is up to week 5, you were just exposed to heat conduction taking place only in one direction. So we use the assumption. So the prime assumption that we used is of 1D heat conduction, where where we assume that our temperature profile is just a function of x only, where x is the direction in which we are looking to evaluate the temperature profile, evaluate the variation in the temperature profile. Okay, so since we are just interested in only one direction, that is the x direction, so that's the reason why we considered. So basically we assume that heat transfer is going to take place in that particular direction only, neglecting the transverse directions in which there could be possible variations of heat transfer. So what we are going to do today is now, so we'll basically we'll increase the dimensionality now. We will say that, okay, now given that we have a conduction problem, what will happen if we have temperature variations taking place in two directions, let's say x or y direction. And in principle, you can apply the method of separation of variable that we will learn or that we will see today. Also, what we have saw, also the glimpse of which we have already discussed in the lecture series, or you have solved a couple of problems associated with that in the lecture series. You can see that the method of separation of variable can also be applied for 3D problems as well. But there are certain conditions on the boundary conditions and the governing equations which needs to be satisfied in order to use the method of separation of variable. But in principle, what we will now look, as I was saying, is that we will now look into 2D heat conduction, where the temperature profile will, instead of it being just a function of x, it will now be a function of, let's say, x and y. And as I said, in principle it can be multidimensional. For instance, it can also be a function of z, but we will stick to just 2 dimensions as of this course, in the interest of this course. So if now my t of x becomes a function of both if the temperature profile now becomes a function of both x and y, this means that essentially now my heat transfer is 2 dimensional. This is obvious because now the temperature profile also varies with x and it also varies with y, which means first of all you need to understand the fact that the governing equation now, let's say we are trying to evaluate the temperature profile. So the governing equation, which is nothing but the steady state heat conduction equation, this now becomes a PD instead of it being an ODE. Okay. So earlier, what we were looking at is that in assuming that it's a steady state heat transfer process, our governing equation, since the temperature was just a function of x, was just an ODE. So we had separate, we had, like known techniques for basically solving those ODEs uh, analytically without invoking any assumptions. But in 2D heat transfer, as you know that the temperature profile is just is a function of x and y. So the governing equation, which is the which is the heat diffusion equation. Let's say I'm writing the heat diffusion equation assuming that it's a steady state uh, and there is no heat generation. So the governing equation then just turns out to be a PD, which is something like this. So it is del 2t by del x2 plus del 2t by del y2 equals to 0. So you can see that when you consider the fact that your temperature profile is one dimensional, this term basically goes away, which means that your T is just now a function of x, and then you recover the linear temperature distribution that we looked into in the previous classes, where we applied the resistance model and all those things to calculate what will be the heat flux and the rate of heat transfer. But now, as you can see, it's a PDE that we are dealing with. So first of all, the first thing first, the changes that you can see is that now the ordinary differential ddx, this just changes into del x, means that it's, so we are kind of writing a partial derivative, which is second order. And this prime reason is that your t is now since a function of two independent variable. So differentiation in t needs to be done with respect to the partial, partial differentiation in t needs to be done with respect to all the independent spatial variable, and that's the reason why we have a del x instead of a ordinary differential operator ddx. Okay, that's the first change that you see. And we can also write this equation, which is this heat diffusion equation written for the spatial case when there is no heat generation and a steady state phenomenon, as an operator which is known as the Laplacian, which is del square t equal to 0, where this del square is known as a Laplacian operator. And in principle, this is how the Laplacian operator will look like, because I have just written this PD in compact form as del square of t. So del square essentially implies that it is in 2D at least, it is just del 2t del square by del 2 by del x2 plus del 2 by del y2. Okay, so this is how the Laplacian operator look like. In principle, this is how it looks like in a two-dimensional scenario. For instance, if you want to extend this to a three-dimensional scenario, your Laplacian operator would look basically like this. So it is just del 2t by del x2 plus del 2 by del y2 plus del 2 by del j. Okay, this is what your Laplacian operator would look like. So in principle, you can say that in 2D heat transfer, your temperature field is basically, so it's a Laplacian equation that you need to solve in if you are trying to solve for a temperature field. So this is one point that you also need to understand. Now, a second instance is where you can have a 2D heat transfer problem with heat generation. So when there is heat generation, of course, you need to understand a couple of things here before actually going on to heat generation, is that this Laplacian equation of for temperature, that is in the case when there is no heat generation and it's a steady state conduction that we are looking at, it's a linear equation. It's a linear equation. The reason why this is a linear equation is can be interpreted from this fact that we just have a derivative of temperature appearing here. without the dependent variable or its derivative being multiplied with one another, and or the squares of it. For instance, we don't have a term like t del t del x, or we don't have a term like t square, or we don't have a term like t square times del square t by del y2. So if you don't have terms like this, then you can make many other nonlinear terms out of it. Since we don't have any nonlinear terms, this equation is essentially linear. And you can also see that t equal to 0 satisfies this equation. So if you just substitute t to be equal to 0, you can see that the right hand side is equal to the left hand side, which means that this is a homogeneous equation. And it's a second order PD that we are looking at. Okay, so these are certain characteristics of the Laplacian equation, of the Laplace equation, that you can see that it's linear, it's homogeneous, and it's second order. Actually, these three characteristics is what enables us to use the method of separation of variable, as we will see very shortly. For instance, if you don't have a homogeneous governing equations, you cannot apply directly the method of separation of variable, but still you can invoke something which is known as superposition, which we will discuss at the end of the discussion today. You can still use the method of superposition because of the fact that your governing equations are linear, and then you can use the method of separation of variable. But in principle, you cannot directly use the method of separation of variable if you don't have a homogeneous equation. Okay, that's something to look out for. For instance, let's say if there is a heat generation taking place, then your governing equation in case of 2D heat transfer, because we are still in the 2D heat transfer scenario, would look like something like this. So you already saw this. So it is just del square t by del x2 plus del square t by del y2 plus q dot by k. This is equal to 0, where your q dot is the uniform volumetric heat generation time. Okay, and it has a unit of watt per meter cube, as we all know, and we have been dealing with this. Okay, so now you can write this equation as a Laplacian of temperature equal to minus of q dot minus of q dot of k. Okay, and this equation has got a special name, I mean the form of this equation. So first of all, you need to understand that this is still a linear PDE. Okay, linear because we just have the derivatives of temperature in the equation, and we don't have we don't have temperature multiplied with its derivative or squares or something like that. So it's still linear, but you can now see that t equal to 0 does not satisfy this equation, because the right hand side is not equal to left hand side, because the right hand side is just a constant, which is q dot by k, and the left hand side is, when we invoke t equal to 0, it is just equal to 0. So although it's linear, the steady state to the heat, heat diffusion equation with heat generation is a non-homogeneous PDE, typically because we don't have a trivial solution in this form of equation. Okay, so it's a non-homogeneous second order PDE. Okay, and again, the reason why it's non-homogeneous is trivial, because t equal to 0 is not a trivial solution here. Okay, whereas in case of the Laplacian equation, where there was no heat generation, we saw that t equal to 0 satisfies this equation uh, in this in this scenario. So whereas the Laplacian equation is a homogeneous equation, this form of equation where t equal to 0 is not a trivial solution, this is known as a Poisson equation. So in the literature, in the mathematics literature, this form of equation is known as a Poisson. This is known as a Poisson equation. And in order to solve a Poisson equation, you cannot directly, apply the method of separation of variable, typically because you don't have a homogeneous governing equation. But still, you can apply if you use something which is known as the method of superposition, which we will see at the end of this discussion. and using the method of superposition, you can apply method of separation of variable in order to solve a Poisson equation in certain scenarios. Not in every cases, I guess, but in certain scenarios you can still apply the method of superposition. And rest assured, in order to solve a 2D heat transfer problem with constant heat generation, you can use method of superposition along with, you know, method of separation of variable to evaluate the temperature profile. And we will see that at the end of this discussion. Okay. But nevertheless, it is still a second order PD. But now you need to understand that the Laplacian equation was homogeneous, whereas the Poisson equation, as you can see on your screen, is essentially non-homogeneous. Okay. So as you know, you are just required to solve for the temperature field, and now you know that your temperature field will be a function of both x and y. So in such cases, there can be the typical problem in 2D Cartesian coordinates looks something like this: that you have a slab, you have a rectangular slab, and let's say you are exposing one of the faces of the slab at a prescribed temperature, let's say T. Uh, So I can say that let's say this is t for all x comma y equal to some b is equal to t naught. So meaning that the uppermost face of this slab is exposed to a non-zero temperature T naught, whereas the temperature at all other faces, for instance, the temperature on this face, the temperature on this face, and the temperature on this face is basically 0. And this is a classical scenario where you can apply, in order to evaluate the temperature profile, because you know that your temperature profile in general now be a function of x and y, because it will have variations along x and it will have variations along y. So in general, your t will be a function of x and y. So basically, in order to solve for a temperature field inside this rectangular slab, you need to solve, in this case, the Laplacian equation. And this is the crux behind using the method of superposition. I mean, the method which we will use today there are many ways of solving the equation, but the method which we will use today, this is heavily popular, and it's one of, I would say, one of the basic methods for solving PDEs, is the method of separation of variable. Okay, so that's what we will use in order to solve for the unknown T of x and y, which governs basically, which is the temperature profile of this plate. So you can appreciate that the governing equation for this scenario, the governing equation would just be Laplacian of t equal to 0, because we don't have a heat generation, which means that the equation that we need to solve is del square t by del x square plus del square t by del y square is equal to 0, subjected to certain boundary conditions that we have, the your temperature here on these faces, this is equal to 0, and your temperature on this face is equal to some T naught. So this is typically what the whole idea behind solving this Laplacian equation. Okay, and of course T0, as I said, this is greater than 0 basically. Okay, meaning that you have imposed a non-zero face temperature on one of the faces, and you are interested to know how the temperature profile looks like. So in order to understand and in order to solve a problem involving such scenarios, we will try to solve this problem, which is asking us to derive an steady state temperature distribution for the case in which we have a rectangular slab where the three faces are maintained at t equal to 0, and the uppermost face, as I have said, is maintained at a temperature A times AX. So you can see that instead of having a constant temperature on the upper face, we are now having a linear temperature profile, which says that the temperature on this upper face is the variation is such that it's a linear variation in the axial coordinate in the x direction. So given this, they are asking us to evaluate the temperature profile, and we will try to solve this problem in detail in order to have a better understanding of the method of separation of variable, and and uh, we will look into the certain nuances of this method as we start to solve this problem. But I hope you can understand that because we have a finite length in x and y, this is indeed a two-dimensional problem. Since the length of the face is a and the width of the face is b, or the height or width or the height, whatever you can infer from it, it is b. We are essentially dealing with a scenario where your temperature profile will be a function of both x and y. Okay, to the otherwise cases where we just looked into the variation in just x direction, because we didn't have a finite length in the y direction, or we assume that there is no heat transfer taking place in the literal direction basically. But in this scenario, since we are having a finite thickness of the slab, finite thickness and length of the slab, and one of the faces is exposed to a temperature which is a linear function in x, if you want to try to evaluate what is the temperature profile or the temperature variation inside the slab, we basically need to look into a 2D scenario, as what we had been discussing in the last 15-20 minutes. Okay, so let's start. But I would also like to highlight one important fact here, that this boundary condition for the top face, what we are saying is that my temperature for all x at y equal to b is some a times x. Okay, so what we are essentially doing is we are prescribing the temperature on one of the faces. Okay, so this boundary condition is known as a Neumann. Sorry, this boundary condition is known as a Dirichlet boundary condition. Okay, I think there is just one T in Dirichlet. Okay, so this is the Dirichlet boundary condition where we are just prescribing the value of the dependent variable. Okay, we can also have a scenario where instead of prescribing the variable itself, we are prescribing the derivatives of the variable. Okay, and such boundary condition, for instance, we are prescribing what is del T by del X at for all x at y equal to b. If we are prescribing this is known as a, so what we are essentially saying is, instead of prescribing the temperature, we are prescribing indirectly the heat flux. Okay, and such type of boundary condition is known as a Neumann boundary condition, uh, where we are prescribing the derivative. So in Neumann boundary condition, as you can see, we are prescribing the derivative of the dependent variable. Okay, so I think that's easy to recognize. So if we are just imposing the variable itself on the faces, it's known as it's called as a Dirichlet boundary condition. And on the other hand, if you are prescribing the derivative of the dependent variable on the faces or at the boundaries, it's a Neumann boundary condition that we are using. And the boundary condition which basically have a signature of both the Dirichlet and the Neumann. This is there. So there is another boundary condition which is known as the mixed boundary condition, where you have both the Dirichlet plus the Neumann. Okay, so the third boundary condition is the mixed boundary condition, where we can encounter a combination of Neumann and a Dirichlet boundary condition. Okay, but mostly in heat transfer problems, we don't encounter mixed boundary conditions, because either the value of the temperature or the value of the heat flux. But knowing two simultaneously is essentially, is difficult. So either you have a Dirichlet boundary condition or you have a Neumann boundary condition in heat transfer problems. Okay. All right. So with that, let's try to solve this problem. So as I said, so this is a problem where we had a rectangular slab where the three faces was at temperature T equal to 0, and the upper face is where we are imposing a temperature which is A times x, that is the temperature on the upper face varies linearly with x. And given this, what we require to find is the steady state temperature distribution of this slab is what we are asked to find. So first of all, we will start off, actually we should start off by writing the assumption, uh, which for this case is kind of a straightforward. So we know that we are dealing with a steady state heat transfer scenario. Uh, and we are assuming that as the problem says, there is no heat generation. There is no heat generation, and you know, constant properties is what we are looking at. Okay, so for instance, the thermal conductivity of the slab is assumed to be constant and not a function of x or time, basically constant you know properties. So just the standard assumptions that we have been using so far. Okay, so using this assumption, as we have already discussed, the governing equation which would govern how the temperature profile of the slab would vary is nothing but del square T by del x square plus del square T by del y squared is equal to 0. Or we have been saying that this is nothing but the Laplacian of T is equal to 0. Okay, so that's the governing equation. Important aspect of this are the boundary conditions. So we'll write the boundary conditions as well. So when you look into the boundary condition, so first of all, you need to understand that had your temperature been just a function of one of the independent variable, for instance, if your temperature is just a function of x, we would just have d2t by dx2 to be equal to 0, and this is just a second order, you know, ODE, for which we just require two boundary condition. Okay, but now since it's a PDE and it's second order in both x and y, essentially we require four boundary condition to close this problem. In principle, these kind of ODEs are known as elliptic ODEs, so we'll not go into the details of this. But for an elliptic ODE, uh, we need boundary conditions in order to have. So for elliptic ODEs in particular, in order to have a closed form solution, we need boundary conditions on the four on all the boundaries of the problem, typically, and not just and generalizing all Laplacian equations, for instance, Laplacian of any variable equal to 0, these are all elliptic ODEs. And in order to, so there is a particular characteristic of Laplacian equation is that you need to define its variable on all the boundaries to uniquely find a solution of the variable precisely. Okay, we will not go into the details of these. So these are so if you take higher courses on PDEs or maths courses, you will learn more on the characteristics of Laplace equation. We will not go into the depths of this, but we will basically, I'll try to put forward certain discussions which I feel are required in order to understand the true aspect of solving a PD, in particular this Laplacian equation. Okay, so as I said, we require boundary condition on the four boundaries. So, and we actually have, because you can see that on the three faces your temperature is equal to 0, and on the fourth face, which is the upper face, we have a temperature which is linearly varying with x. Okay, so so then what do we have? So the first boundary condition you can say is that your T for all x at y equal to 0, which is the lower face, this is equal to 0. Your second boundary condition is that, let's say, your upper face is equal to your a times x. Okay, the third, the right, and for the right and the left face we have T for x equal to 0, for all y this is equal to 0, this is the left face, and your T for x equal to a, for all y this is also equal to 0, this is for the right face. Okay, so just to clarify, this is for the lower face, this is for the upper face. Okay, this is for the left face, and this is for the right face. Okay, so in principle, as I said, what we have is we are trying to solve this temperature profile for the slab, and we indeed have boundary condition on its four boundaries basically. So from the principle, it means that we can have unique solution for this Laplacian equation. And if you are more interested in knowing the characteristics of Laplacian equation, you can prove that your solution to the temperature profile will be such that it will not exceed its value at the boundaries. This means the Laplacian operator is kind of an averaging function, okay? So I mean, just to give you an idea, so you can prove using certain mathematical tools is that your solution will not be more than a times x, basically, that you can actually prove, because this is a property of a Laplacian equation, and in principle Laplacian is kind of an averaging function, and since it's an averaging function, you cannot have values which are greater than the extreme values of the problem, okay? So your values will lie between 0 and a times x in true sense, in true practical sense, if I want to say, okay? So this is, so that's why you can, if you are more interested, you can look into the certain properties of Laplacian equation. First of all, as I said, it's elliptic. Laplacian problems are always elliptic, which means in order to find closed form solutions, you need to have values on all the four boundaries. Second, it's kind of an averaging function. So these Laplacian equations are kind of an averaging function. So the temperature profile you will calculate will not exceed the boundaries. So its value will not exceed the will not exceed the values from the boundaries. Basically, it will always be in between the extremum values from of the problem, that of the boundaries. Basically, that is something that I want to convey. Anyways, these are some extra information that I want to give. So given this, the reason why this method is known as the method of separation of variable is because we will now assume, and as the name suggests, this is the most important step of the problem. So what we'll do is we'll now assume that the temperature profile which we are trying to calculate, T of x, this is a function of x times a function of y. Okay, and this is the main crux of method of separation of variable, and as the name suggests, that is the reason why it's called the method of separation of variable, because we have written a function which is a function of both x and y as a product of two functions which are just sole functions of the individual independent variables. Okay, and then after writing t of xy equal to some g of x times f of y, what we need to do is we just need to substitute this 2 of a into the governing equation, which is, I guess, here is written as 1. Okay, and when we substitute, so let's see what we have. So we have del 2t by del x2, that's the first term, and if we substitute, this just becomes del 2 by del x2 g of x times f of y. But remember, this is a partial derivative with respect to x. So any function of y, this will just be a constant in this scenario. So this will just come out of the derivative. So this means it just becomes f of y times, now the del will convert to d because this is just a function of x. Okay, so this will just become d2g by dx2. Okay, I hope this is clear. In the same spirit, if you write del 2t by del y2, and then if you write the form of t that we are actually assuming, then this just becomes g of x times f of y. And the same conclusion goes here, is that this is a partial derivative with y, so a function of x, this will just come out of the derivative basically. So this then becomes g of x times d2f by dy2. Okay, all right. Then what we need to do is we are just substituting, so we just need to replace these terms with these terms and this term with basically this term in one. So we just have, so what do you have? So the equation was del 2t by del x2 plus del 2t by del y2 equal to 0, and then we are replacing this del 2t by del x2 and del 2t by del y2 by invoking the form that we considered. So it just becomes f of y times d2g by dx2 plus g of x times d2f by dy2, and this is equal to 0. Okay, I believe so far we're going nice and easy, and things are clear up to this point. All right, so now what we'll do is we will divide. So let's say I'm writing this equation as 2b. So what I will do is I'll divide 2b by f of x, sorry, I think that's g of x. We'll divide this by g of x times f of y. Okay. And when you do this, you can see that the first term, since you are dividing by f times g, so here the f and f will cancel, and from here the g and g will cancel. And you can see that we are basically getting a term like 1 by g of x times d2g by dx2 plus 1 by f of y times d2f by di2, and this is equal to 0. Okay. And if we do a fair, you know, bit of rearrangement, I mean, I'll just take this term to the other side. Then, I can write this term as 1 by f times. So we'll not repeatedly write f of y and g of x. We will, so whenever you see an f, you just need to realize that this is a function of y, and whenever you see a g, your g is just a function of x. So I'll just write f and g's instead of, always writing the variables in the brackets, basically. So this then becomes 1 by f times d2f times dy square, and this becomes 1 by g times, sorry, I'm taking the 1 by g to the other end, so this becomes minus of 1 upon g times d2g by dx2. Okay. And here is, I would say, the most important step in method of separation of variables. So what we have seen is that this is a function of, so what is this? This is just a function of y, right? Because we have said that your t is g of x times f of y. So f is just a function of y, and d2 df by dy2 is also a function of y, which means this is just a function of y. Okay. And on, the right hand side, this 1 by g times d2g by dx2, in fact, minus 1 by g times d2g by dx2, this is just the function of x. In fact, I should write function of x only and function of y only. Okay. But what we are saying is that a function of y is equal to a function of x. Now here is a dilemma, basically. We are saying that the left hand side is a function of y and the right hand side is a function of x, and then we are saying that a function of y is equal to a function of x. This is only possible, and this is something that is important, this is only possible when these two separately has to be equal to a constant. Otherwise, no way a function of y can be equal to a function of x. Okay. The only way if it is possible is that these two separately has to be equal to a constant, and that constant for this case we'll call it as lambda square. Now, you will see that lambda is actually known as the eigenvalue of this problem. The reason why this is known as an eigenvalue, I'll explain to it. I hope you understand, but anyway I'll explain to it at the end, towards the end of the solution. But to this end, you need to understand that this lambda is, so this is known as an eigenvalue. Okay. I'll write it down anyway, but this is known as the eigenvalue. And you should have asked me that why I'm not writing a minus lambda square and just a plus lambda square. So the answer would be, see, the lambda, so the square I'm writing because I'm saying that the constant in general without the loss of generality is positive. That is, it gets satisfied for all the values of lambda. But overall, it can be negative or it can be positive. And you could have equally argued that why didn't I write it as minus lambda square? What's the harm in doing that? Now, I would say that proceed your problem by writing minus lambda square. You will see that the nature of, so the boundary conditions that we are trying to solve will not be satisfied if we are writing a minus lambda squared here. Okay. And I will prove you otherwise that actually writing lambda square, the boundary condition, we can actually impose the actual boundary condition in this problem. And if you write minus lambda square, you will see that you are unable to fit in the boundary conditions. Okay. And that is, and that's actually how, and this actually explains how difficult solving PDs is if you don't have, a overall complete knowledge of the problem. Because if you are naively solving this problem without actually looking into how the boundary conditions are, or how basically the physical nature of the problem will kind of look like, choosing the form of eigenvalue is difficult. Okay, and if you choose the wrong eigenvalue at the end of the problem, you will see that, oh, that the boundary conditions are not making sense, and then that, which means that my eigenvalue, the choice of my eigenvalue is actually wrong, and then you again need to come back and then you choose the other form of the eigenvalue. Okay, and trust me, for different PDEs or for different physical scenarios, this eigenvalue, it can be minus lambda square as well. So this is actually, so the choice of the eigenvalue in order to solve PDEs using method of separation of variable is actually governed by the physical nature of the problem and the boundary condition. Okay, and this is something that I want to convey, and I hope you will realize as and when you practice more into like solving PDEs. And that is why, PDEs, there is very difficult to make any general formulation for solving PDEs. Okay, and this is one of the reason, and that's the reason why I said at the beginning that solving PDEs are essentially difficult with respect to solving ODEs, because it's very highly sensitive to the problem that you're actually solving in. All right, so that's it then. We're just writing these two. So the only possible way, as I said, is that this should be equal to a constant. So now what we need to do is we now need to solve for the values of f and g basically. So now, and in the hindsight, you can see that essentially we are trying to convert this PDE into an ODE, and that's because we know solutions to ODE. That's the harsh reality that we are kind of doing here. Okay, but you can also understand that the path we are taking is that we are essentially trying to convert the PDE into an ODE. So as I said, we'll now solve for the f and g. So what I will say is that my 1 by f times d2 f by dy2, this is equal to lambda squared, which means that I can write it as d2 f by dy2 minus lambda squared times f. This is equal to 0. And this is a solvable ODE, right? Because you know how to solve these kind of ODEs. It's a second order linear, homogeneous ODE. So the way you solve this, just a reminder, is that you consider f to be some e power m times y, and then what you do is you just substitute this, so you basically get something like, so if you substitute this form into this equation, maybe I should name the equation. So let's say this is 2c, let's say this ODE is 3a, and let's say this form that we are considering, this is 3b. So if you just substitute 3b into 3a, what you will get is d2f by dy2 will be just m squared times e power my minus lambda squared e power my, and this is equal to 0. And since e power my cannot be equal to 0, because again we are not looking to get any trivial solution, this just means that your e power, so I'll just take e power my common, and then m square minus lambda squared, which is equal to 0. And the fact is that this e power my, this cannot be equal to 0, because if my e power my becomes 0, this means that my f basically becomes 0. And if my f becomes 0, I say that my temperature, which is just g times f, and if f is 0, this means that my T essentially comes out to be 0. But that's the trivial solution, right? And we don't want the trivial solution, because you already know that the physically T equal to 0 is not a possible solution, because you are kind of imposing non-zero temperature on the upper face, basically. Okay? Which means that in that all these stories, just if you pick the dots, it just means that e power my cannot be equal to 0, which then means that m squared minus lambda squared is equal to 0, which means that your m is equal to plus and minus of lambda. Okay, and then your solution for f, which is just a function of y, will be equal to e power m1y, because it will be linearly independent of the two roots. So basically it will be e power m1y times e power m2y, and then this will be just e power lambda y plus of e power minus lambda y, but there will be a constant here. There will be a constant. The reason why there will be a constant is because these two solutions can be linearly independent of each other. So this will be just C1 times e power m1y, and this would be C1 times e power lambda y plus C2 times e power minus lambda 2. That's the, so again, because you got the two roots for m and you are assuming the solution of this form, and the only possible way is that these two roots are linearly independent. So this would be some any generic constant times the first root e power times m1y. So m1 is equal to lambda, and then some arbitrary constant C2 times e power minus lambda 2y. Okay. So that's it. That's the solution for f of y. And but still remember, we still need to evaluate the constants c1 and c2, which we will be doing very shortly. Okay. So maybe I name this as equation 3c, and maybe I name this as equation 3d. Okay, let's quickly solve for g as well, because we know that that this minus 1 by g times d2g by dx2, this is equal to lambda square as well. So this is then minus of 1 by g times d2g by dx2, and this is equal to lambda square. And then you assume the same form of solution for g, because it's the same form of equation. It's ODE, it's second order, it's linear. So you can then assume that your g of x is some e power, let's say we are calling it as n now, or maybe something else, maybe l times x. This is what you're solving. And then if you substitute this form, I'll not do the steps for this because it's just repetitiveness with respect to the first case. So if you substitute this form, you will end up getting a solution for g of x as g of x equal to some c3 cos lambda x plus c4 sine lambda x. It's very simple. Just substitute this form here, do the same steps as we did. You will end up getting this form, and then use something which is, and you can use the identity that e power I theta is equal to cos theta plus I sine theta. Uh, if you use that identity, you can write this as cos sine solution basically. Okay, so that's it. That's the solution for g of x, and maybe I'll call this as phi. So now, as I said, we need to evaluate these constants c1, c2, c3, and c4. Okay, and what we'll do is, in order to evaluate the constants, there are 4 constants that we need to evaluate, and we have 4 boundary conditions. So it's a closed problem that we are dealing with, as I say. So let's do this. Then let's first try to evaluate this C3 and C4 from this problem. So for this, let's use the boundary condition on x that we have. So we know that x equal to 0, we have t equal to 0, and at x equal to a, we have t equal to 0. Okay. So let's use this. So from boundary condition, I guess this would be what boundary condition. So these two boundary conditions on the left and the right face. So using, I'll write it down. So using the boundary conditions for the left and the right face. Okay. So what do we have? We have t at x equal to 0 for all y. This is equal to 0, but we are assuming that my t is equal to g times f basically. So I can then write that my g at x equal to 0 times a generic f of y, this is equal to 0. And then again the same argument. My f of y cannot be equal to 0 because this is just a generic function of f, generic function of y. Because had this been equal to 0, then this will just render t to be equal to 0, which is a trivial solution, and we are not looking into the trivial solution, which means the only possibility that we can have is g at x equal to 0 is equal to 0, and we have the solution for g, right? So this is the solution for g, which means my g at x equal to 0 then becomes C3 to be equal to 0, because at x equal to 0, this basically goes out, this basically goes to be equal to 1, which means that C3 is equal to 0. Okay, this means we have evaluated one of the constants. Okay, so maybe I'll call this as 4a. Now using maybe this is, yeah, this is not the right phase. This is, yeah, sorry, this is the, sorry. So this is for the left phase that we have written. And if you write the same for the right phase, okay, you can then say that my t at x equal to a for all y is equal to 0, which then again draws the same conclusion that my g at x equal to a times f of y, and this is equal to 0, which means that since my f of y cannot be equal to 0, this means that g at x equal to a, this is equal to 0, and then your g at x equal to a is just now c4 times sine of lambda a, and this is equal to 0, because we already know that C3 is basically equal to 0. That is from 4a that we are writing. Okay. Which means that now we encounter two possibilities. Either C4 is basically equal to 0, but then again this is not possible because C3 is already 0, and had C4 been equal to 0, this means that my entire G would just turn out to be equal to 0, because G is nothing but, you know, C3 times cos lambda x plus C4 times cos sine lambda x. And we know that, you know, C3 is already 0, so had C4 been equal to 0, then this G would basically be 0, which again would mean that T is 0, which again, the same point, the trivial solution, and we are not looking for that. Okay. Which means that the only possibility again here that can arise is that my sine lambda a has to be equal to 0, which then means that my lambda a should be equal to n times pi, and then my lambda is basically equal to n pi by a. Okay, so the unknown lambda, that we call it as the eigenvalue, simply comes out to be equal to n pi by a. Okay, and this would be valid for n equal to 1, 2 even infinity basically. Now this is where I would again come to the term eigenvalue. The reason why you call this as an eigenvalue is that you can see that the solution is satisfied not for all values of lambda, but for certain discrete values of lambda, which is of the form n pi by a. Okay, only values of the form n pi by a for the, you know, value of lambda will give solution to this particular problem, and that's the reason why this is called as an eigenvalue problem. And this is actually, the name eigenvalue comes from the fact that there exists a trivial solution which we know, and apart from the trivial solution there are certain possible values on which, you know, we can get, you know, solutions to this, to the governing equation, and those certain values, those are known as actually the eigenvalues. Okay, and that's the reason why we call this lambda as an eigenvalue of this problem. So now this means that your g of x, sorry, that your g of x is just some, you know, c4 times sine lambda x, uh, c4 times sine lambda x, and we know that my lambda is equal to n pi by a times x basically. All right. Okay, so we are done in solving for the g's. Now let's try to solve for the f's, and let's try to do that. So the solution of f, as we saw, is something like this. So f of y, so as we calculated it, so f of y, but before that, let's name this. So let's say we name this as what, 4a, maybe we'll call it as 4b. So as I said, your f of y was c1 times e power lambda y plus c2 times e power minus lambda y. Okay. Now let's use the other two boundary conditions. Let's see what we can get from the other two boundary conditions. So if we use the boundary conditions on the lower phase, we have that p for all x at y equal to 0 is basically equal to 0, which then again I can write it as g of x times of f at y equal to 0 is equal to 0, and g of x cannot be equal to 0, which means that my f at y equal to 0 is equal to 0. And then we know the solutions for this, right? So at y equal to 0, this becomes what? This becomes C1 plus C2 to be equal to 0. Okay? Which means that C1 is basically equal to minus of C2. And maybe I can call this as 5a. Okay? Therefore, my form of f of y will look something like this. So it is C1 times e power lambda y. Okay? But C2 is minus of C1. So I'll write it as minus of C1 times e power minus lambda y. Okay? And then, I can write this as, if I take a C1 common, I can write it as e power lambda y minus e power minus lambda y. And what I will do is I will now use a property. So you know that sine hyperbolic lambda y is nothing but e power lambda y minus of minus e power lambda y by 2. Okay, because that is the property of the sine hyperbolic function, which means I can write this e power lambda y minus e power minus lambda y as 2 times of sine hyperbolic lambda y. Okay, and if I use this property over here, then my f of y is just 2c1 times sine hyperbolic lambda y. Okay, but we still require to find c1. Remember that. And maybe I'll call this as 5b. All right, then let's try to write the equation for t then. So what do we have? So then t of x comma y, this is just equal to g of x times of f of y. And we now have individual solutions for g and f. We know that my g is c4 sine n pi x by a. So my g is basically c4 times sine n pi x by a. Okay, and f of y is 2 times of c1 times sine hyperbolic lambda, which is n pi by a times y. Okay, and what we'll do is, see, these are just arbitrary constant, right? 2c1 times c4. So basically I'll write these constants as c5, which is equal to just 2c1 times c4, and this is just, so I'm just writing this as another constants, which is just c5, and then this then becomes c5 times sine. So this is your t x comma y, this is your t comma y, and then this becomes c5 times sine of n pi x by a times sine hyperbolic n pi y. Okay, I think I made a mistake here in y, in the y boundary condition. Or no, maybe, yeah, okay, it's fine, I guess it's fine, yeah. Anyways, so this is just sine n pi y by a, basically. Okay, and remember, we still now require to find this c5, but you now need to understand one thing, that this solution that I wrote, this solution that I wrote, this is true for multiple values of n. This is true for n equal to 1, n equal to 2, and this is true for up to n equal to infinity. Because remember, your lambda is n pi by a, and this is true for n equal to 1, 2, 3, going up to infinity. Okay, so in principle, I should write this as summation over all n, where n going from 1 to infinity, some c5n. Okay, because this constant will appear on each and every values of n, and then this would be sine n pi x by a times sine hyperbolic n pi y by a. Okay, and this is what your true sense of the solution would look like. Okay, and maybe I'll call this form of the solution as what, as 6. Okay, all right, but still we are left in calculating this c5n, and just for the sake and for the ease, we will not write C5n repeatedly. We'll just call it as maybe some dn's. Okay, it's just because it's just another constant. Okay, so then this will just be just I am writing it once again. This will just be summation from n equal to 1 to infinity dn's times sine n pi x by a times sine hyperbolic n pi y by a. Okay, and maybe I should name this as equation 6. Yes. All right. So then we are just left with evaluating the value of the constants dn's. But this is again, I would say this is the third most important step in applying this separation of variable. So let's see now that what is the boundary condition left. So we know that the boundary condition for the upper phase is the fact that my t for all x at y equal to b is equal to a times x, where a is just a constant. Which means if I impose this boundary condition, let's call it as 6a, and if I impose this 6a onto the form of the solution 6, then I should get ax to be equal to, so I'm writing this at y equal to b, which means that this would just turn out to be y equal to b, and then this becomes ax, the because I know that at that point my temperature at that phase, my temperature is just a times x. So then this becomes ax equal to summation n equal to 1 to infinity dn times sine n pi x by a times sine hyperbolic n pi b by a, because I'm writing this at the upper phase, which is y equal to b. But then how do we still calculate these dn's is I would say the third most important you know point of using basically the method of separation of variable. Okay, uh, I would stop here for a couple of minutes. I'll just fill my cup with some water. Up to this point, if there are any doubts, you can ask. Okay. All right. Sorry for the interruption. So yeah. So as I said, now we are just left to evaluate these dns. But remember, the the point is that this dns needs to be evaluated at each and every values of n, because this is how it comes from. Because as I said, this is an eigenvalue problem which gets satisfied for some specific values which is equal to n pi by a basically, which means that you need to evaluate dns for n equal to 1, let's say n equal to 2, n equal to 3, and so on and so forth. So then again, how do we then evaluate this? Okay, and this is what this is where we will use a principle of something which is known as orthogonal functions. And so what you are writing is essentially is that if you have a closed loop at this equation, what you are doing is that you are writing a known function which is a times x in this case as a summation, as a series of orthogonal functions. Okay, and in principle, this is so it is the power of orthogonal functions is that any functions can be written as a series solution of the orthogonal functions, and that is from where the Fourier series and the Fourier coefficients and the Fourier transform actually comes from. But in in true sense, if you have orthogonal functions, you can write any functions in space as a series solution of these orthogonal functions, and that's what you have actually, and that's what we have actually knowingly or unknowingly did here by using the boundary condition on the upper face. Now the question is that then how do we calculate these coefficients? Actually, these coefficients are known as the weight functions of the orthogonal functions, and we evaluated these coefficients dn's or the weight functions by using something which is known as orthogonality principle. Okay, so we will use something which is known as orthogonality principle. Okay, which says, so the orthogonality principle actually says is that if I have an orthogonal function, let's say the sine functions or the cos function, then if I integrate these orthogonal functions up to, within the period, let's say L is the period. For instance, if I integrate sine mx times sine nx dx within, let's say, the period L, or it can be a integer multiple of the period L, then this is equal to 0 when m is not equal to n. Okay, and this is equal to L by 2 when m is equal to n basically. Okay, so I hope you can understand that when my m becomes equal to n, this value will just spit out to be equal to L by 2, and when in all other scenarios, for instance, when m and n are not equal and it is equal to any other values, this integration would just be equal to 0. So we will use this principle which is known as the orthogonality principle into this form of the series expansion here in order to evaluate these weight functions or the constants dn basically. Okay, so in order to use that, what I will now do is, maybe I'll call this as 6b, and what I will do is I will multiply, in order to use, I repeat, in order to use the orthogonality principle, I will multiply equation 6b uh, with sine. So what I should do, I should multiply this by sine, something like sine m pi x by a. That is what I should multiply it. So I'll multiply this by sine m pi x by a. Okay, and just multiplication will not do, we need to integrate it over its period. Okay, so and integrate it over the period. Okay, which in our case will be from 0 to a basically. Okay, so that's what we will do. So we will integrate it from 0 to a ax times, but remember we are multiplying by sine m by x by a. Okay, and so the left hand side again then would become integral 0 to a summation over n dn's times what, sine n pi x by a and then there is this sine m pi x by a, and then remember there is a constant term which is this hyperbolic term sine hyperbolic n pi b by a basically, okay, times sine n pi b by a, and we are integrating this with respect to dx. Now the good thing is these dn's are not a function of x, and so is this sine hyperbolic, sorry, this is the hyperbolic term. So the good thing is, as I said, these dn's and this hyperbolic term, these are not, functions of x. So then I can just write this as integral 0 to a, okay, ax sine m pi x by a dx, and then this would be summation over n dn sine hyperbolic n pi b by a, and then we have this integration from 0 to a, okay, sine n pi x by a times sine m pi x by a. But using the orthogonality principle, as I said, because we know that integral 0 to L sine m pi x sine m pi x sine n pi x, this is 0 when m is not equal to n, and this is equal to L by 2 when m equal to n. So using the orthogonality principle here, okay, so using the orthogonality principle here, this integration would be 0 when m is not equal to n, and you can basically show that this integration would be a by 2 pi, because it would have been L by 2, okay, but since there is a pi factor here, that's why this pi factor will come here. So this integration would be a by 2 pi when m is basically equal to n. So only when m is equal to n, this integration will be a non-zero value, which is a by 2 pi, which means that this integration is just equal to a by 2 pi for n equal to m. So then I can write this as what? Then I can write this as integral 0 to a, okay, ax times sine. Now n is basically equal to m, so I'll just write n to be m only. So then this becomes n pi a by x, okay, times dx, and then this is summation over all n dn, and this is just a by 2 pi basically. And then there is a hyperbolic term as well, which is sine hyperbolic n pi b by a, which means that's it. I know the value of dn. So my dn's for each values of n, I can now just remove the summation sign, because we know that this needs to be satisfied for all values of n. So then my dn's just becomes 2 pi by a times integral 0 to a ax sine n pi a by x dx by sine hyperbolic n pi b by a. That's it, guys. dn's are completely known to us. Why? Because this integral is just known. So just apply integration by parts. This integral will just be a constant of a basically. Okay? Because you're integrating this with respect to dx only. Just you need to apply integration by parts. That's it. So that's the value of dn's that we have evaluated. Maybe I should write this as equation 6c. Okay? So that's it. So the solution then is t of xy is equal to summation over all n's dn's sine n pi x by a sine hyperbolic n pi b by a. Okay. Sorry, hold on. I think, yeah, sorry, this is sine hyperbolic y by a, because this is what your t of x is essentially, uh, yeah, because that's what t of x is, right? It is sine n pi x by a, sine hyperbolic n pi y by a, and then the unknown dn's is just this one that we just calculated. Okay, so this is, maybe I should call it a 7, the final form, where the unknowns, dn's, with which we evaluated it by using orthogonality principle, is just this 2 pi by a, then this integral from 0 to a ax times sine n pi a by x times dx by sine hyperbolic n pi b by a. That's it. That's the solution for your temperature profile. And maybe I should, you know, box this. So, couple of things that you need to understand. First of all, why did we use the principle of superposition? What was the governing equation that we solved for? How the temperature field basically looked like, and how did we invoke the orthogonality principle in order to evaluate this constants dn? I hope you realize that this dn is just a constant because this integral is a known integral in x. Okay, just use integration by parts. I have not done this integral. You are, you know, more capable enough than me to basically use integration by parts to basically do this integral. Okay, and you can see that this integral will just be a function in a. So in principle, dn's are just the constants in a and b's, and these constants, you can see these are satisfied for each and every values of n, for n equal to 1 to 3 up to infinity, and 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 this is what the full temperature profile would would essentially look like. Okay, so yeah, so that's the idea, and this is a good demonstration of actually applying the method of superposition of variable. Okay, now one question that I would like to address here is that, had we why didn't we choose minus lambda square in the eigenvalue. Okay, now the question is from the answer itself. Okay, see, the variation is such that I have a zero temperature here and a zero temperature here, which means that I can have a sinusoidal variation in the x, and then I have a prescribed variation of temperature when I move from y0 to y. So had I choose a minus lambda square, here, then the solution that I would get will be such that I will have a sinusoidal variation in y, okay, which is zero on the two extremums, and a hyperbolic variation basically along the x, which is not actually what the boundary condition is, right? Because the boundary condition is such that I have zeros here, which means the only fit I can do is a sinusoidal variation in the x, and a prescribed variation in the y, because I know that my y is basically zero here and my y is kind of a times x over here. And that is the reason why we wisely choose a lambda square such that I can have a cos. So the sinusoidal variation comes from cos and sine functions, right? So that's why I had a cos sine variation in the x direction, and a hyperbolic or an exponential variation in the y direction, such that the boundary condition fits in. So had you solve this problem naively and choose a minus lambda square instead of choosing a plus lambda square, you would see that you will end up getting a point where the boundary condition doesn't fit in, and then again you need to go back and then choose the other value of the eigenvalue, which is plus lambda square. So it's a hit and trial, basically what you did in the choice of eigenvalue. So that's why I say that the choice of eigenvalue in separation of variable while we are solving PDEs is extremely sensitive to the boundary conditions that we are solving in and the physical nature of the problem that we are looking at. Okay, that is one aspect of using method of separation of variable. The second point I would like to highlight here is that, see, this method of separation of variable was possible because we had a homogeneous boundary condition, because in multiple points I said that we are not looking for trivial solutions. Now had there been a non-homogeneous equation, you will see that you cannot apply method of separation of variable. You start this problem just as it is, now choose a non-homogeneous equation, you will end up getting eventually to certain instances where you can just have to put your hand and say that, oh, the method of separation of variable can't be applied. For instance, as I said, if you solve the following problem, that there is a heat generation now taking place. So if you just solve the same nature of the problem, but now you say that there is a heat generation, taking place with uniform heat generation, which means that now your PDE will is basically something like this. So it will be del square T by del x2 plus del square t by del y2, which is equal to minus of q dot by k. And this is what the Poisson equation that we discussed in the beginning of the discussion. This is just the Poisson equation. So here, if you just, just just say that your t of x of y is equal to g of x times f of y, and then if you just substitute, this will basically not work. The reason why this will not work, as you will see, you just do it and you will see that you have a non-homogeneous term, you have a non-homogeneous equation because of this term minus q dot by k. So then how do we basically solve this? So this equation can still be solved, using method of separation of variable, but what we will do is we will use something which is known as actually known as method of superposition. So the method of superposition is applicable because of the fact that your G, that is the governing equations, are still linear in nature. Okay? Because your governing equations are linear, my entire solution can be written as a linear combination of two solutions. And that's what the method of superposition actually relies on. Okay? So what I will say is that my t of xy, what the method of superposition does, I will write my t of xy as, let's say, a term t1 of xy plus a t2, which is just the function of x, basically. Okay? And then if I just use this form, let's say maybe I'll call this equation as 1, and maybe I'll call this as 2. And if I just substitute, 2 in 1, I can see that my equation is then becomes del square t1 by del x2 plus del square t1 by del y2 plus t2 t1 by dx2, and then this becomes equal to minus q dot by k. Okay, and then what I can say is that my t1 will satisfy del square t1 by del x2 plus del square t1, sorry, this will be t2 because I have written the solution in this form. So then I can say that del square t1 by del x2 plus del square t1 by del y2, this would be basically equal to 0. This is what the equation t1 of x comma y satisfies. And also I can say that my d2 t2 by dx2 equal to minus q dot of k, and this is what my t2, which is just a function of x, satisfies. Now the good part is this is just an ODE and we know the solution. Basically it's a parabolic solution. We had been solving this multiple times, so this is just an ODE. And the best part is this is now just become, so the equation in t1 just becomes of the form del square t1 is basically equal to 0, which now became homogeneous, to be precise. So you have essentially converted using this form, which is known as the method of superposition. You have essentially converted a non-homogeneous linear PDE into a homogeneous, into two equations, which is a homogeneous, linear PDE and a second order, ODE, which is again linear. Okay, so you can now apply, method of superposition here. You can now apply method of superposition here to basically solve for T1, and then this equation is trivial, right? We know how to solve, ODEs, parabolic ODEs, basically. Just you need to solve for this. So this is I would say this is an easy solution because it's just the parabolic profile that you will get. And then your final solution, which is T of x comma y, is just the linear superposition of T1 of x comma y plus T2, which is just a function of x. That's it. So it's kind of a superposition that we do, and that's the reason why this is known as the method of superposition, basically. So this is a way of solving Poisson equation using method of superposition, where you try to extract a Laplace equation out of it, and then
dump the other, source term. So this term is essentially known as a source term because it's a known constant term. So you dump the source term by making an extra ODE out of it, okay? Which, is easier to solve, and we all know the solution of solution for ODEs. So as I say, you can evaluate the solution for T1, by solving the Laplace equation now, and you can apply method of superposition of variable, sorry, method of separation of variable, which we did in the last, which we had been doing in the last hour or so, and then you can solve this, this ODE as well, and the complete solution is just the solution for these two, basically. That's it. So you will have a series solution for here as we just solved, and then we'll have just a parabolic solution here, which is kind of like the the 1D problem that we had been solving in this course for multiple times. And that's the beauty of this method, which is known as method of superposition. Now, you need to understand that this assumption, this will break down if we have a non-linear PDE. Okay, so the method of superposition does not work for non-linear PDEs, and you need to understand this because if you have a non-linear PDE, you cannot if you use this assumption. I mean, if you are writing t as a function of t1 plus t2, this will no longer work because because the PDE itself is non-linear. Okay, so for non-linear PDEs, method of superposition does not work. Okay, because the reason why it does not work is you assume this solution and then fit into the PDE, and then if you just club all the terms, you will see that you will just retain certain extra terms, which is not again the original PDE that we were actually dealing with. Okay, because that's so the two equations that we wrote here, if you add these two, this we should regain the original PDE. Okay, but had there been a nonlinear PDE, if you just club the separated parts and then see that are we getting the original PDE or not, you will see that in case of nonlinear PDE, you will not get the original PDE. Instead, you will get certain extra terms in the PDE, and that's the reason why you cannot apply method of superposition in case of non-linear PDEs. And then the only result is that you need to solve. There are multiple ways. So either you can, so first of all you need to solve the PDEs numerically, and one of the approach is known as finite difference method, where you basically need to discretize the PDEs. We'll not discuss this in this course because it is not the scope of this course. There are many other techniques. For instance, there is something which is known as spectral method, which is again a numerical method only, but the way of discretizing using spectral method is different. There is also something which is known as finite volume approach, finite element approach. Commercial softwares like COMSOL or ANSYS, they use these techniques only. For instance, ANSYS uses finite volume approach, COMSOL uses finite element approach, and you can write your own code using finite difference and using these techniques basically. Okay. Spectral method uses something which is known as Galerkin's method and things like that. So we'll not basically go into the details of this numerical method because this is not the point of this course. But yeah, if you have a nonlinear PDEs, then you need to you know look into numerical solution. Basically, there are very few analytical solution, and to the best of my knowledge, there aren't no analytical solution which can actually solve give you analytical results to uh, to these PDs basically. And that's the thing. So that's what I tried to convey here through this discussion session. So I believe this is a little bit involved session in terms of the maths that we did, but I also hope that you tried to understand the nuances, and I tried to reflect the nuances of these techniques, specifically the method of separation of variable, and how does it work, what's the Laplace equation, what is the Poisson equation, why we are dealing with a 2D heat transfer case, what is orthogonality principle, and the series solution, eigenvalues, and things like that. And finally we ended by discussing the method of superposition, and and in what cases the method of superposition actually works on, and things like that. So we'll again meet tomorrow. As I said, that's the usual class where we'll be discussing this week's contents, which is week 7. which is the transient, heat transfer analysis. And we'll be looking into something which is known as lumped capacity analysis and things like that in this in for tomorrow's discussion. But I hope you understood this discussion hour. We will, as I said, we will again meet tomorrow. That is the usual timing from 3 to 5. I think you're already posted. That has been already communicated to you via emails and through the course website as well. And that's on the usual timing with on the usual link that we will meet. And yeah, so thank you for joining. If there are any questions related to this these concepts of concepts that we discussed today, I understand the maths was a little bit heavy, but yeah, but this that therein lies the beauty of it, right? Sometimes you need to dig deep, basically, to understand the nuances. So I hope you understood this, and if there are any questions, please post it in the discussion forum. In general, if there are any questions related to the assignment, please post it in the discussion forum, and I'll be happy to address them. And or else we'll again meet tomorrow at the usual time from 3 to 5 at the usual link, and we'll be discussing the contents of week 7, which is transient heat transfer analysis in conduction. Okay. Um, till then, thank you very much for watching these videos. If there are any doubts, as I said again, please post it in the discussion forum. We will meet tomorrow again from 3 to 5. Thank you very much, guys.